Hi. Back in lecture 10b of Differential Equations in Linear Algebra, we talked about a linear transformation from a lower dimensional space to a higher dimensional space. We saw that that example, at least, could not possibly be onto, which makes intuitive sense, and was most likely to be one-to-one as it was. The image was not all the codomain, but the kernel was just the zero vector. Here in this lecture, we're switching it around. We're doing a linear transformation from a higher dimensional space to a lower dimensional space. We're going to see that there's no way such a function can be one-to-one, but that typically, most likely, it is onto. Okay? As I mentioned in a lecture 11a, this is now lecture 11b, you're going to see connections now between differential equations and linear algebra to some degree, and I'm going to again point those out here. And as we continue in the next 2, 3, 4, 5, 6 lectures, these connections are going to get stronger and stronger. All right, so let's consider a linear transformation from R5 to R2, from a higher dimensional space to a lower dimensional space. In 10b, we did from R2 to R5. It was an example that arose from what's called a least squares problem. I'm not going to talk about any application here. I'm just going to pretend I've got a linear transformation from a higher dimensional space to a lower dimensional space, and I'm just going to go ahead and write its equation right away. And I pretty much made the matrix that you see here at random. Okay, it wasn't completely random, but I pretty much did it that way. I'm writing it in this formula in all these ways, as I often do, to emphasize the key concepts that we've talked about so far. Let me re-emphasize those. First of all, you've got this equality right there saying that, hey, t of x, the linear transformation, evaluated at the input x, which is a vector, in this case a 5-dimensional vector, is going to have a formula that involves a matrix times the vector x. A is a matrix. And that matrix better have 5 columns since x is 5-dimensional. X is a 5 by 1 matrix, also a 5-dimensional vector. We've been typically writing our vectors as column vectors. In order for A to be able to be multiplied on the left times x, it better have 5 columns. Now it also happens to have 2 rows. It didn't have to have 2 rows. It could have 1 row or 3 rows or 4 rows or whatever. But to actually do this multiplication, the second number here, the number of columns, must match the first number here, the number of rows. Those match so you can do the multiplication. And the result is going to be a 2 by 1 matrix. You look at the outer numbers, which is the same as a 2-dimensional column vector, which is what you see there in the end. The next equality emphasizes the meaning of a matrix times a vector that I've been emphasizing. To do this matrix times this vector, you take a linear combination. This is a linear combination, linear combo of the columns of A, columns of the matrix capital A right there. Notice 2, 3 is the first column, -4, 2 is the second column, 0, 1 is the third, 6, -5 is the fourth, 2, 0 is the fifth. Where the entries from the vector, x1, x2, x3, x4, x5, are the weights in front of the vectors, sometimes called coefficients, to create this linear combination. A linear combination of vectors, you just add up scalar multiples of the vectors. That's what a linear combination of vectors is. But then, by the definition of how you multiply vectors by scalars and how you add them component-wise, this can be simplified to that. I could have written the formula right away like that if I wanted to, and notice there's no constants being added here, as I've emphasized for linear transformations. But I wanted to emphasize all these key concepts that we've been talking about so they stay clear in your mind. It's so important to really make sure these concepts are clear in your mind. Otherwise, you're just going to be confused. You need to make sure these are all clear. We can then ask the same questions as usual, our same questions, and these are useful questions. And there are connections to differential equations, as we will see. Yes, there are. What is the image of t as a linear transformation? What are the set of all outputs? Is it all the codomain or not? Is it onto? Is it all of R2? I hope it makes sense that it probably is, since we're going from higher dimensions to lower dimensions, that it's likely to be onto. We're kind of collapsing the 5-dimensional space to a 2-dimensional space. What is the kernel? What's the set of all vectors in R5 that get mapped to the 0 vector in R2? I hope it makes sense that there should be, in a sense, a lot of them. More than one, more than just the trivial solution, more than just the 0 vector. And so T is not going to be 1-to-1. I could ask the question, but the answer is going to be that it's not. I'm telling you the answers. But these questions can be answered for sure by doing more row operations, like we did in lecture 10b. As I just mentioned, such a function like this from a higher dimensional space to a lower dimensional space, it turns out, is guaranteed to not be 1-to-1. Though in all likelihood, if you're picking these numbers for the matrix at random, which I somewhat did, the probability that it is onto is close to 1, if not equal to 1, when you're really truly doing it randomly. If you really can do it randomly, we won't get into what it means to be truly random. I could make examples where it's not onto, if I was careful, but I'm not doing that here. So how do we do the row operations? What I'm going to do is a sort of a general augmented matrix, where the right-hand side numbers for the corresponding system of equations are arbitrary, y1 and y2. In lecture 10b, I think I used the letters A, B, C, D, and E for my arbitrary letters. But more consistently in this kind of situation, we're going to use y's, just like we're using x's here. And more consistently from now on, we're going to use subscripts for both the x's and y's. The x's are your input vectors and the y's are your output vectors, in a sense. We're really thinking about what are all the possible things this could be, in a sense, setting this equal to y1, y2, or the vector y, and trying to solve. So we're trying to solve this general system of linear equations by looking at an augmented matrix and doing row operations. Elementary row operations, they're called again. There's 3 versions of them. One is there's swapping rows, that's allowed. Sometimes that's helpful. A second row operation is multiplying any row by a non-zero constant. And the third row operation is called the row replacement operation. Multiply any given row by a non-zero constant. Actually, it can be 0 in this case. And add it to another row and put the answer in that other row. Multiplying by a constant, that plain row operation without adding needs to be non-zero, because if it were 0, then you get a row of zeros and that messes things up. So, and we're trying to get to what's called reduced row echelon form. We only have 2 rows here. We're looking to get a leading one, hopefully in the very first column there. That 2 we'd like to make it become a 1. So the first row operation I'm going to do is multiply the first row by 1/2. To make that a 1, that a -2, this a 0, this a 3, this a 1, and this would become y1 divided by 2. And I'm leaving the second row as is, not changing that. Now I have a leading one in the first row. Locations of leading ones are also called pivot positions. And then the one there itself is called a pivot. The 2 here is also in a pivot position and could be called a pivot because we are going to be able to get a leading one there. The next step is to get zeros below that leading one in the first row. Now there's only one number below it. There's 3 right there. I'd like to get a 0 there by doing a row replacement operation. Multiply row 1 by -3, add it to row 2, and put the answer in row 2. That'll get a 0 there. What will go there? Well, -2 times -3 is +6. +6 plus 2 is +8. There'll be an 8 there. The 0 will not affect anything. Add it to the 1 after multiplying it by -3, and I still leave a 1 there. 3 times -3 is going to be -9. -9 plus -5 is -14. 1 times -3 is -3 plus 0 is -3. This thing times -3 is going to be -3y1 over 2. Add it to this, I'll get -3y1 over 2 plus y2. And get this. Again, I like putting these dashed lines, and I recommend my students do that to Remind yourself that these are augmented matrices corresponding to equations where what's to the right of the lines are on the right-hand side of the equations. Yeah, 0, 8, 1, negative 14, negative 3, negative 3y2 over 2 plus y2 is what went in the second row after that row replacement operation. Got a 0 there. I'd like to get a leading 1 there. And that would be good because it'll be to the right of the leading 1 above it. The leading 1 above it is to the left of the leading 1 in this column right there. To get a leading 1 there, I just multiply row 2 by 1/8. Now actually, so I am going to reduce row echelon form here, but actually, as it stands, this is enough to say, to understand that no matter what y1 and y2 are, there's going to be a solution. Because this line is not all a bunch of zeros and then that. You're going to be able to solve for for x1 and x2 in terms of some free variables here, x3, x4, and x5, and in terms of these things. There will be solutions no matter what y1 and y2 are. That will guarantee that t is onto, that its image is all over 2. You could stop here for that, but now I want to go all the way to reduce row echelon form. So again, the next step is to multiply row 2 by 1/8. 0 times 1/8 is 0. 8 times 1/8 is 1. 1 times 1/8 is 1/8. Negative 14 times 1/8 is negative 7/4. Negative 3 times 1/8 is negative 3/8. And this thing times 1/8 gives you this thing. Check it. This is echelon form. The last step for reduced echelon form is to also get zeros above any leading ones. There are no numbers above this leading one, this pivot position, but there is a non-zero number above this leading one in this pivot position, this negative 2 there. So I want to get rid of that negative 2 by by multiplying row 2 by 2, adding it to row 1 and putting the answer in row 1. That will not affect this one because of the 0 there, but we will get a 0 here, which is what we want. 2 times 1/8 is 1/4. 1/4 plus 0 is 1/4. We'll get a 1/4 there. Negative 7/4 times 2 is negative 7/2, which is negative 3.5, plus 3 is negative 1/2. This thing times 2 will be negative 3/4, plus 1 will be positive 1/4. And then we'd also need to do it with this thing here, to the right of the dashed line, multiply that by 2, and add it to this. And in that case, we will get this, and you can check that. Okay? Got a 0 here like we wanted. Yeah, this was 1/4, this is negative 1/2. Yeah. This times, again, 2 is negative 3/4 plus 1 is 1/4. Multiply this by 2 and add it. For example, you'll get y2 over 4, which we do, and negative 3/8 plus y1, negative 3 y1 over 8 plus y1 over 2 does simplify to y1 over 8. Okay? All right, that is now in reduced row echelon form. You don't have to try to get 1s and 0s here. There's nothing more to do. You've got a leading 1 in each row. This is good enough to stop now. And now if we think about trying to write the solution set to the system in parametric vector form, as I mentioned last time, you'd want to remind yourself that this does correspond to a system of equations. x1 plus 1/4 x3 minus 1/2 x4 plus 1/4 x5 equals this. You'd want to subtract 1/4 x3 from both sides, add 1/2 x4 to both sides, and subtract 1/4 x5 from both sides. This is a place where lots of people make mistakes. You need to imagine moving those over to the other side. And so the sign changes. Many people forget to make the sign change. Okay? Don't be a person like that. Make the sign change. Think about it. Here you've got x2 plus 1/8 x3 minus 7/4 x4 minus 3/8 x5 equals this. You're going to be moving these things to the other side, so you subtract 1/8 x3 from both sides, add 7/4 x4 to both sides, add 3/8 x5 to both sides. So again, the signs will change. And the system of equations it corresponds to is this. And the parametric vector form of the solution set is this. I skipped a number of steps there. Now think about it, okay? Think about looking at this and comparing it with this. x1 is negative 1/4 x3, that's where this comes into play, negative 1/4 in an x3, plus 1/2 x4, that's where this comes into play, x4 plus and times a half, minus 1/4 x5, that's where this comes into play, the x5 and the negative 1/4. But then you still have the constants, so to speak, on the right-hand side, y1 over 8 plus y2 over 4. Those can be combined here. Now I could separate those into two vectors as well, but I'm not bothering. We're almost to the connection to lecture 11a about particular solutions and homogeneous solutions. Maybe you can even see it. x2 is negative 1/8 x3, that's where these two things come in, x3 times negative 1/8, plus 7/4 times x4, that's where these two things come in, plus 3/8 times x5, that's where these two things come in. x1 and x2 depend on x3, x4, and x5. x3, x4, and x5 are called free variables. They are free to vary over the entire real number line. But you also have more. You got, well, essentially x3 equals itself, x4 equals itself, and x5 equals itself. So you've got to have a 1 here in the third spot with the x3, a 1 here in the fourth spot with the x4, a 1 here in the fifth spot with the x5. And zeros elsewhere. If you think of the solution initially as a 5-dimensional vector like this, and you write x1 and x2 in terms of all the other stuff, but x3, x4, and x5 are themselves. Yeah, this is related to the differential equations content from lecture 11a, a connection. This right here is like a YP, a particular solution. Should I call it YP? Maybe not. Well, maybe capital YP. Or maybe it would make more sense to call it capital XP, since it's an X vector, so to speak. XP, these are X's, even though you see Y's in there. And this summation right here, where x3, x4, and x5 are arbitrary, you might call an XH, solution of the corresponding homogeneous equation, where the right-hand sides are 0. y1 and y2 are 0. That would make this a 0 vector here, and you could just write the solution like that. And that would be a description of the kernel of the linear transformation. Just like YH in the differential equation was really a solution of the associated homogeneous equation, which written in linear operator form, I said in lecture 11a, could be thought of as a linear transformation. Are you happy? Connection. It's a pretty deep connection in a sense. x1 and x2 are not called free variables in this context. They are called basic variables. If you ever take operations research and do what's called linear programming, you'll, in that context, talk about basic variables, and there's some deeper connections there too. Look at this here. What? Is there a way to visualize this geometrically? These are 5-dimensional vectors. They're sitting inside 5-dimensional space. So right off the bat, I guess you can't imagine it. Literally at least, but you can imagine it maybe by analogy. Now we've got 3 free variables. Does this describe some sort of 3-dimensional plane in 5-dimensional space? If y1 and y2 are non-zero, this would not go through the origin. If they were 0, it would go through the origin, if you picked x3, x4, and x5 to be 0. And it turns out you can think of it that way, though you can't literally draw it or literally imagine it. You can still work with it that way, and that still gives you some insights into some things. This is a 3-dimensional, often called a hyperplane, 3-dimensional plane, is sitting inside 5-dimensional space. Talk about that again here. Now, what does all this mean about this particular, we're talking about this particular linear transformation where I picked the A matrix with numbers that were somewhat random. From R5 to R2, it means image of T, like I mentioned, is all of R2 and T is onto. Second, as I've mentioned, for a given Y in R2, the set of points in R5 that gets mapped to Y, just like I just said, is some sort of three-dimensional hyperplane and sitting inside five-dimensional space. The fact that there were three free variables in the parametric vector form of the solution set is not enough to guarantee this, though you might say it makes it likely with randomly chosen numbers. To guarantee it, those vectors next to x3, x4, and x5 in the parametric vector form need to be what are called linearly independent vectors. I haven't defined what linearly independent means yet. That's soon to come in 2 or 3 or 4 lectures. In fact, you could even say the hyperplane is parallel to the kernel. And in fact, like I mentioned, the kernel is the same set where the first vector that was constant when y1 and y2 were constant is gone, because I'm taking y1 and y2 to be 0. The kernel is this, and somehow in a higher dimensional space they would be parallel to each other. The opposite perpendicular angles can come into play in higher dimensional space here to try to make sense out of that. Also, like I mentioned last time, you can describe this a little bit more succinctly without the set builder notation, the set of all things like this, such that these numbers range over R. With this notation, the span of these 3 vectors. Span means, the span of these 3 vectors means the set of all linear combinations of them. See this come up a lot. It is an important thing in linear algebra, this notation for span. It's not just saying these 3 vectors are in the span. It's saying this whole thing represents this entire set, which is an infinite set. The set of all linear combinations is what the span is. And the span idea will generalize as well. We're going to ultimately talk about in, again, 2 or 3 or 4 or 5 lectures is what are called vector spaces. And all these ideas, kernels, images, spanning, all generalize. Even till when you're talking about linear operators too, and differential equations. And when I'm talking about the connection between linear algebra and differential equations here, it really is in terms of these linear transformations as operators. It's not going back to the very first lecture where I emphasized the main connection is change of coordinates. That's still later to come, and that's our most important connection. Take a breath. The second main topic of this lecture is composite linear transformations. Composing functions. Suppose T is a linear transformation from Rn to Rm, and S is a linear transformation from Rm to Rp. Can I combine these linear transformations? Yes. Oops, this is an N here. Sorry. T maps from Rn to Rm, putting the T above the arrow in this case, and S maps from Rm to Rp. The domain of T is Rn, the codomain is Rm. The domain of S is Rm, and its codomain is Rp. If you first do T and then do S, you get the composition going from Rn to Rp. S compose T means do T first, then S. You work from right to left. Maybe you've seen this circle notation before, maybe you haven't. Back 30, 40 years ago when I was young, everybody, even in maybe junior high, saw the circle notation for function composition, certainly in high school. It seems like they don't teach as much these days. You're combining these 2 functions to get a new function. It really is a binary operation, just like addition and multiplication are binary operations. It's taking 2 things and getting a new thing, combining them to get a new thing. So this is a binary operation. It's not commutative. S circle T, S compose T is not in general equal to T compose S. And in fact, depending on the values of N, M, and P in this case, you can't even necessarily do T compose S. Yeah, since the codomain of T is the same as the domain of S, we can compose the linear transformations to get a new function, S compose T, from Rn to Rp. The domain is Rn, the codomain is Rp, defined by this formula. S compose T of X equals S of T of X. And I wrote that out in words to really emphasize it. You do talk about composition of functions in your past. You've talked about it. And in calculus, it was very relevant, for example, with the chain rule. When you look at this thing, there's an inside function and an outside function, right? T of X gets done first, order of operations. That's the inside function. S of whatever gets done second. That's the outside function. If you're going to differentiate this, you need the chain rule. I'm not going to differentiate it. All right. The circle notation is the symbol for the composition. This expression is its formula. But these days it seems like people just focus on this and not that. But I want you to know about this. That comes up in my blog. Infinity is really big. And we do this for all x in the domain, which is Rn. Is this new function also a linear transformation? You would think it should be. This is another reason to not add constants in the linear transformation formula. We want this composition to be a linear transformation. It better be operation preserving. Given, let's call them u and v in Rn, the domain, and scalars alpha and beta in R, you should be able to give a reason for each quality that I'm about to show you to confirm that this composition is operation preserving. It is OP, which always reminds me as a Generation X person, I think that's my generation, I never paid much attention to that. OP reminds me of Ocean Pacific, which was an old clothing line back in the 80s. You can look it up. And is therefore a linear transformation. Here we go. S compose T of a general linear combination of these two vectors. And you can generalize this to an arbitrary linear combination of a finite number of vectors. But this is good enough. Alpha u plus beta v. By definition, I'm giving you the answers here, of S compose T equals this. It's S of T of alpha u plus beta v. Now use the fact that T is a linear transformation to modify the inside here to be this. T of alpha u plus beta v, T of that linear combination, is the corresponding linear combination of T of u and T of v. It's alpha T of u plus beta T of v. Paying attention to every single word I say? You kind of have to. T of this linear combination is the corresponding linear combination with the same weights alpha and beta of the images of u and v under T, T of u and T of v. But this is S of another linear combination. S is linear. We're assuming S and T are linear here. So I can once again factor out the alpha and beta out of that. I can get the corresponding linear combination with the same weights alpha and beta of S of this vector and S of this vector. Alpha S of T of u plus beta S of T of v. But then I can use the definition of the circle operation to say those things are these two things. And that does it. S compose T of this linear combination, alpha u plus beta v, is the corresponding linear combination with the same weights alpha and beta of S compose T of u and S compose T of v. Feels like you're not doing anything significant here. In fact, mathematicians sometimes just call this symbol pushing. But you actually are doing something very significant. Okay? You're verifying that this function, this composition, is operation preserving using assumptions about S and T being operation preserving, and using the definition of what composition means. And yeah, that's a significant fact. And this generalizes to those vector space ideas as well. How is it related to matrices? Again, suppose T goes from Rn to Rm and S goes from Rm to Rp. By the way, I'm not saying, what of these numbers are bigger or smaller. N, M, and P are arbitrary positive integers, 1, 2, 3, 4, 5, 6, etc. So we're talking in general here in the abstract. Then we know, but what we talked about, I don't remember which lecture 8B maybe, I'm not positive, 9B, something like that there are corresponding matrices that implement these linear transformations, and the direction of the number of the M, P, and N go in the opposite. There's a P by M matrix A and an M by N matrix B such that S of Y is A times Y and T of X is B times X. Think about this carefully here. Let's go with S first. S goes from Rm to Rp. Inputs are M-dimensional and outputs are P-dimensional. So A better be P by M because Y is M-dimensional. Y, oops, this should be bold-faced. Y is M-dimensional. A is M by, get this right here. A is P by M. Y is M-dimensional. P by M times M by 1, you can multiply it. The M's match in the inner numbers. And the result is P by 1. It's P-dimensional. A times Y. B times X. B is M by N. X is N-dimensional in Rn. M by N, you got to multiply it by an N by 1 vector. To get an M by 1 vector, the answer is in Rm. And in fact, if, as we wrote before, we can write the columns of these matrices in these ways, and think carefully about these dimensions here, this is related to the definition of matrix multiplication. As a linear combinations of the columns with the entries of the vectors as weights. B, remember here, is M by N. N columns, so there you see B1 through Bn. Each of these B's is M-dimensional. Bi, I represents an arbitrary subscript 1, 2, 3, etc. through N. I could have said I is 1 through N here. But each of these is M-dimensional because there's M rows and N columns. You see N. And A is P by M. P rows and M columns. M columns, you see an M there. Each of the A's is P-dimensional. Take the time to think about this all the time when you see it, to think about whether things are right, whether it's consistent. And I do make mistakes here, so hopefully I haven't made a mistake. And you can write these things, these multiplications as linear combinations of the columns with the corresponding entries of the vectors as weights. B times X is a linear combination of the columns of B, these bold-faced B's, with the entries of X, X1, X2, through Xn unbold-faced as the weights. See why it's important to keep track of what's a scalar and what's a vector? The Xi is the ith component of X. You've got X1, X2, X3, etc. through Xn. And S times Y is A times Y is a linear combination of the columns of A, with the entries of bold-faced Y as the weights. Yi is the ith component of Y, Y1 through Ym. Hang out here, what's our purpose? What are we trying to do here? We're trying to see, does S compose T have a matrix? And if so, what is it? And if you know what matrix it is, would that mean you know how to multiply matrices? And the answer is yes. Therefore, since matrix multiplication is also linear, I've never verified that before, operation preserving, but because T of X equals A times X, or in this case T of X equals B times X, since linear transformations are operation preserving, so are their corresponding matrix multiplications. also called linear. Linear in this context means operation preserving. We have S composed T of X, and purposely mixing red and blue here, is S of T of X. The T's are in red and the S's, T's and X's are in red and the S's and A's are in blue. But T of X is B times X. And B times X is this linear combination here. Goes down there. And then I got A times this thing. This is like a linear combination there. The linearity, the operation preserving, comes in here. I get the corresponding linear combination with the same weights x1 through xn of AB1, AB2, AB through ABN, like this. I changed the B's to being blue here. Don't let that bother you. Could have kept them red, I guess. But what is that? That's a linear combination. x1 through xn are weights. These things, AB1, AB2 through ABN, are vectors. You could put them in a matrix as columns, like that. And this matrix right here is going to get multiplied by x to get the output of the composition. This is going to be the definition of the product A times B. We want this to equal A times B times X, because that would just make intuitive sense that when you compose the linear transformations, maybe we should multiply the matrices. A times B. A times B, evidently then, is going to be a new matrix whose columns are capital A times the columns of B. And we can do the multiplication here. A, remember, is where P by M. B is n by n. The inner numbers match of the matrix on the left. Its number of columns is the same as the number of rows of the matrix on the right. And the answer has got to be P by n. This matrix here better be P by n. Well, it's got n columns. There's an n there. Are these p-dimensional vectors? Yeah, because A times a vector is p-dimensional. Oh boy. An example will help. Okay, we should define the matrix product as this P by n matrix right there. We're about to do an example, and this example is our last slide. There we go. I'm not going to take the time to check this in detail. Okay, I'm not going to go through this slowly. I'm going to go pretty quick. You should pause the video and check this. Check all this. Let A be this 4 by 2 matrix, and let B be this 2 by 3 matrix. So you can compute AB because the number of columns 2 of A equals the number of rows 2 of B. And the result is going to be 4 by 3. And if I use the definition at the bottom of the last slide, the columns of the product should be AB1, AB2, AB3, where B1, B2, and B3 are the columns of B. B1 is the first column, 1, negative 2. Look at this. B2 is the second column of B, negative 1, 3. And this product gives you this. And B3 is the third column of B, 2, negative 3, and the product gives you this. Right? Notice I'm writing these things as linear combinations of the columns of A. Like right here, 1, 3, 5, 7, 2, 4, 6, 8 is what the vectors you see here and here. The 1 and the negative 2 are the weights that come from this vector right there. Take the time to check all this. Hopefully I did not make a mistake. Hence, put all these final vectors in a matrix. A times B is this 4 by 3 matrix. This first column is this vector. The second column is this next vector. And the third column is this next vector. Let me just end by saying this can be related to dot products. Maybe you've learned how to multiply matrices in the past, and maybe you learned it in terms of dot products of rows with columns. If you learned that in the past, I'll encourage you to check that this is the right answer that way. If you haven't learned it, you may want to just think about it, do some investigation as to what that means. we'll review that and emphasize it in lecture, what would it be, 12B. Thanks for watching.